Hello and welcome to another NGen Math 7 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 6, Lesson 9 on an interesting property of inequalities. Now in the last lesson, Lesson 8, we solved two-step inequalities and we did them by using the properties of inequalities. And the properties of inequality were really the same as the properties of equality that essentially said, look, you can add or subtract whatever you want from both sides and the inequality will remain true. And you can multiply or divide by a positive number on both sides and the inequality will remain true. But there is one thing about inequalities that's different than equalities in terms of their properties, and we're going to explore that today. Eventually you're going to have to kind of memorize this extra property of inequalities, and then it will arise occasionally when you have to solve an inequality. So let's kind of jump right into it and talk about solving inequalities. Now, before we get into those, we have to make sure though we can really just take a look at numbers that have signs on them, positives and negatives, and talk about whether one number is greater than or equal to another. Now, one thing I'd like to remind you, okay, because this can be tricky when you have positives and negatives involved. At the end of the day, if you've got a number line, right, like this, then any number that lies to the right of another number is larger than it, okay? And that's why like 0 is greater than -5, because 0 lies to the right of -5. That's why -7 is less than -4, because -7 lies to the left of -4. If you ever have any problems with those, especially if you live in a cold climate, think about temperature where it could go negative. You know, -5 degrees is colder than 0 degrees. They're both really cold. You know, and now if you live in Southern California, you're like, I didn't even know there were negative temperatures. All right, anyway, let's get into exercise number 1. The numbers -6, -2, 2, and 6 are plotted on the number line below. Place a greater than, less than symbol in each circle to make the statement true. All right, this should be a piece of cake. I just want you to put a less than or a greater than symbol in each one of those circles to make the statement true. And remember, look at that left-right comparison if you need to. Why don't you go ahead and do that now? All right, well, obviously the first one's a piece of cake because they're both positive numbers. So the plain fact is 6 is greater than 2. All right, now in the case of -2 and +2, let's put it this simply. Every negative number is less than every positive number, all right? So -2 is less than 2. Where it gets a little bit complicated is -6 and -2, right? Because again, it kind of feels like -6 should be greater than -2, but it's not. Because -6 lies to the left of -2, -6 is less than -2. And to make even matters worse, you know, when we're comparing 2 and -6, again, it really feels like that 2 should be somehow less than -6, right? Because 2 is less than 6. And yet, 2 lies far to the right of -6 on the number line, so 2 is definitely greater than -6. Now, before we explore this kind of interesting property of inequalities that equality doesn't have, it is really exceptionally important that if I give you two numbers, you know, one positive, one negative, or both negative, both positive, whatever, that you're able to correctly say whether one is greater than or less than the other. Let's move on. All right, now, again, remember, in the last lesson we explored the properties of inequality. But inequalities, as I've mentioned, have one remarkable property that equalities, in other words, equations, do not. We're going to explore that in exercise number 2. Let me bring it up right to the top. Here we go. Given the true equality 8 equals 8, and the true inequality 12 is greater than 4, do the following to both sides of them and state whether they continue to be true or change to false. All right, so yeah, let's take a look. So, first one, let's add 3 to both sides. Let's first do it to the equality. If I add 3 and I add 3, right, I'll get 11 equals 11. Yep, I think that's still true, right? We'll just use T and F for true and false. Let's do the inequality. Let's add 3 to both sides, and we get 15 is greater than 7. I'm pretty sure that's still true. All right, so far, it looks like in this situation, the inequality is working just like the equality. Let's keep going. Let's subtract 2 from both sides. All right, so if I subtract 2 from both sides of this equality, I'll get 6 is equal to 6. That's very much still true. And if I subtract 2 from this inequality, I'll get 10 is greater than 2. Again, still true. So in this case, the inequality and the equality are working out the same. Let's keep going. All right, let's multiply both sides by 2. Times 2 times 2. That gives me 16 equals 16. Definitely still true. Now let's do times 2 times 2. That will give me 24 is greater than 8. Still true. So I'm not seeing much difference here. Let's do divided by 2 as well. Divided by 2, we get 4 is equal to 4. Still true. Let's see, divided by 2, 6 is greater than 2. Still true. Well, so far, if we've seen some kind of difference between inequalities and equalities, inequalities and equations, it's not shown up here. So let's just be very clear. I can add the same number to both sides, and a true equation remains true, a true inequality remains true. I can subtract the same number from both sides. True, true. I can multiply a positive number on both sides. True, true. I can divide a positive number on both sides. True, true. Right? So now let's take a look at the next set of 4. All right, let's multiply both sides by -3. Now remember, a negative times a positive is a negative, so in this case I'm going to get -24 is equal to -24. Still true. Now let's multiply both sides by -3 here. Sorry about the crowded nature of it. And we've got 12 times -3 is going to be -36 is greater than -12. Hold a second. Let's talk about this one a little bit. -36 is greater than -12. Think about where those two things would be on a number line. That's actually false, right? -36 would lie far to the left of -12 on the number line, right? You'd pass -12 and just kind of keep on going. So now this true inequality has now become false. So here is the first exception, right? This is the first time I see a situation where all of a sudden I've done exactly the same thing to both sides of the inequality and it switched from being true to false. Let's divide both sides by -2. All right, so let's divide by -2, divide by -2. Remember, a positive divided by a negative is a negative. So I'll get -4 is equal to -4. That's definitely true. Now let's divide both of these by -2. 12 divided by -2 would be -6. 4 divided by -2 would be -2. And again, right, -6 lies to the left of -2 on a number line. I mean, look back at exercise number 1, right? So this is now a false inequality. All right, well, let's multiply by -10. Let's do times -10 times -10. That's going to be -80 equals -80. Still true, right? Times -10 times -10. It's going to be -120 is greater than -40. And again, that's false, right? -120 lies well to the left of -40. And finally, let's divide by -4. Positive 8 divided by -4 is -2, so we'll get -2 equals -2. That's true. Here, if I divide by -4 on both sides, 12 divided by -4, let me just put a little dividing line here, is -3. And 4 divided by -4 is -1. And -3 is not greater than -1. That's also false. So in this entire bottom row, we're now seeing inequalities behave different than equalities. And what is the common sort of denominator or the common thing in each one of these? Well, we either multiplied or divided by a negative number. We didn't add, we didn't subtract, we didn't multiply or divide by a positive number. In all those cases, an inequality that remained true continued to remain true. So let's take a look at exercise number 3. What seems to be happening to a true inequality when you multiply or divide both sides by a negative number? Test on the true inequality below by dividing both sides by -3. All right, so what seems to be happening to a true inequality when we multiply or divide both sides by a negative number? Well, it seems to become false. All right. Now, let's just see, because in that other case, we kept like comparing a positive number to a positive number, right? So we had like 12 is greater than 4, all right? But maybe that's the only time it actually happens. Here we've got 15 is greater than negative 12, right? And there's no question about that. 15 lies far to the right, of negative 12, which lies far to the left of 15. I'm going to divide both sides of this inequality. Let me write it out larger. 15 is greater than negative 12. I'm going to divide both sides by negative 3. Right? 15 divided by negative 3 will become negative 5, whereas negative 12 divided by negative 3 is a positive 4. And that is most certainly false. So yeah, when I divided both sides of this inequality by a negative number, it changed something that was true into something that was false. And look, this is why it happens, right? We know that when we multiply or divide by a negative, it switches the sign of whatever we're operating on, right? Think about that for a moment. You know, if I've got, 8 and I multiply by negative 2, it becomes negative 16. If I've got negative 8 and I multiply by negative 2, it becomes positive 16. Literally, if you compare two numbers on a number line and you multiply or divide by a negative, the entire number line flip-flops. It literally, the positives become negatives, the negatives become positives, and the two numbers in terms of left-right orientation have now reversed. You see, if I've got two numbers and I just add something to both sides of them, they just do this. Or if I subtract something from both sides of them, they just do that, right? They literally just move in lockstep with each other, and the one that was on the right, or the one that was on the right from your perspective, continues to be on the right even after I've shifted them. And the same thing is true when I multiply by a positive. They might go like this, but they don't switch positions. But that's what they do when you multiply or divide by a negative. That is the interesting property of inequalities. And let's take a look at it in one more exercise before we actually start solving some inequalities using this property. Exercise number 4. Consider the inequality negative 3x plus 8 is less than negative 13. Letter A, given the two values of x below, determine which one is a solution to the inequality. Show your work. All right, well, you already know how to check whether values of x are solutions of the inequality by taking them and substituting them into the inequality and seeing if it makes it true. So take a few moments right now and figure out, which one of these two is a solution to the inequality. All right, let's go through them. I'm just going to move this a little bit out of the way. So I'm going to do negative 3 times positive 2 plus 8 is less than negative 13. Negative 3 times positive 2 is negative 6. Plus 8 is less than negative 13. Negative 6 plus 8 is 2. 2 less than 13? No. 2 is not less than negative 13. Which probably means that 10 is a solution, but let's just make sure. We've got negative 3 times 10 plus 8 is less than negative 13. Negative 3 times 10 is negative 30. Plus 8 is less than negative 13. Negative 30 plus positive 8 is negative 22, as some of those things cancel. Negative 22 is less than negative 13. You bet it is, because it lies to the left of it. So x equals 10. Now there are many solutions to this inequality, but of these two, x equals 10 is a solution and x equals 2 isn't. But let's say we rewound to the last lesson, right, where we were solving inequalities exactly the way we solved equations. Let's do that in letter B. Let's take a look. Solve the inequality like you did previously. All right, so let's pretend we never had the discussion in exercise 3 or 2 about this special property of inequalities. Let's just solve this like it worked exactly the way an equation does. All right, so we'd get negative 3x plus 8 is less than negative 13. I'd subtract 8 from both sides. Now just be careful here. Subtracting 8 is the same as adding negative 8, so this would be negative 21. And then if I divided by -3, I would then get x is less than, remember, -21 divided by -3 is +7. Now, there's a mistake here. I really want to point that out, especially to math teachers who are like, you've just made an error. So my point is, right, if inequalities worked exactly the way equations worked, this would be the answer. And then all values of x that are less than 7 would be solutions to this inequality. But look at the second part of this. What happens if you don't switch the direction of the inequality? So in other words, really, when we divide by a negative on both sides, we really, to make that inequality not become false, we actually have to flip-flop it. So if I don't switch it, if I just keep it as less than all the way through, then 2 should have been a solution and 10 shouldn't have, right? So in other words, what happens if we don't switch? Well, then the wrong value of x from A would be a solution, right? 2, which is less than 7, should be a solution, and 10 shouldn't if this was correct, right? And yet we know that 10 is the solution, or one of the solutions, and 2 isn't. So what's the moral of the story? After all of that, the moral of the story is, when we're dividing or multiplying both sides of an inequality by a negative, you must switch the direction of the inequality. In other words, a less than would become a greater than would become a less than, to keep the inequality true, all right? If we divide or multiply both sides of an inequality by a negative and we don't flip-flop the inequality, then our solution set will literally be the opposite of what we're looking for. You know, if the solution's like x greater than 7, we would end up with x less than 7, right? And that could be a little problematic. You're not only not finding the answer, you're finding the opposite of the answer. So anyway, let's see how all of this plays out in exercise number 5. All right, let's take a look. For each inequality shown, do the following. Solve the inequality, list some values that make it true, and graph its solution on the given number line. Now, we did this a bunch in the last lesson. The only difference between this and those is that we're going to eventually divide both sides by a negative, forcing us to flip-flop the inequality. So let's play around with that. All right, here we go. Negative 2x plus 11 is greater than 19. The first thing I'm going to do is subtract 19. Now notice, I'm not in any way, shape, or form flip-flopping the inequality because I've subtracted. Subtracting and adding keep an inequality's direction the same. But as soon as I divide by -2 on both sides, that greater than symbol must become a less than symbol. And in this case, x is less than -4, right? So again, very, very important. This is the first time we've ever seen this property, first time we've ever really applied it in solving an inequality. As soon as I have this inequality, which originally was a greater than, and I divide both sides by -2, to keep it a true inequality, I must switch to less than. So x is less than -4. What are some values that are less than -4? Well, -5 is, -6 is, -7. Keep in mind, so is -4.1 or -4.01, etc. All right, so just like kind of previous work, we want to circle the -4, and we want to draw an arrow to the left. Or if you prefer to do it above the number line, put a little open circle above the -4 and draw an arrow to the left. All right, let's take a look at another one. Letter B. 10 minus 4x is greater than or equal to -18. Now again, this one could be written in a rather confusing way. So you might want to use the commutative property on the left-hand side. We're not solving an inequality at all. We're just doing a little bit of expression manipulation. Use the commutative property on the left-hand side to rewrite this as -4x plus 10. And again, I haven't used that property of inequalities here. I'm literally using the commutative property of addition to rewrite that thing. But now this one plays out identical to letter A, so why don't you pause the video and try to finish it. All right, let's do it. So the first thing I'm going to do is I'm going to subtract 10 from both sides. Again, be a little bit careful here because I've really got negative 18 plus negative 10, which is going to be negative 28. Now here comes that interesting property. I'm going to divide both sides by negative 4, and because I'm dividing by negative 4, that inequality is now going to switch to a less than or equal to, the equals is still there, and then it's going to be 7 because I have a negative 28 divided by a negative 4. So, what values solve that? Well, since it's less than or equal to 7, then we've got numbers like 7, 6, 5, etc. All right, in which case we're going to put in a filled in circle on 7. And, whoops, wait, yep. Greater than, yep. And it's going to go to the left. So I just wanted to make sure. Or we fill in circle here, and we do it over. All right, so let's summarize. Inequalities are very, very similar to equalities. We can literally do almost anything we want to both sides of the inequality, and the inequality remains true. You can add whatever you want, whether it's a positive or a negative number to both sides. You can subtract whatever you want from both sides. You can multiply or divide both sides by a positive number all you want, and that inequality will remain true. But as soon as you divide or multiply both sides by a negative, and let me be honest with you, it's almost always division by negative. It's very rarely a multiplication by a negative, but it could be. But as soon as you multiply or divide both sides of an inequality by a negative number, you must switch the direction of the inequality for it to remain true. All right, and we're going to see that a little bit more in the next lesson. For now, I just want to thank you for joining me for another NGen Math 7 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.